So I can't tell you how great it is to finally be here to kick off GeoWeek for multiple reasons. The obvious ones are obvious, but what might not be as obvious is how this event represents the evolution of several events that have taken place over the years and really shaped entire industries. The insights and understandings that have separately impacted the AEC, geospatial, and 3D communities are all now right here. That's part of the reason our intersection of the geospatial and built world tagline that you can see all over the place is so instructive. Because GeoWeek represents a true intersection of tools, technology, and people at the highest levels. The crossover is an essential element of what both of our keynotes are going to be talking about today. Because technology that took humans to the moon and back isn't just about one thing. Figuring out what it means to collaborate using new tools like VR isn't just about the technology. This intersection is about so much more than a single person, single innovation, or a single industry. And while I can't imagine many of the people in this audience are focused on physically going to the moon, hearing from somebody who is should help you understand what it means to approach your own moonshot goals in new ways, thanks to the intersections you can see all across GeoWeek. As program manager in the Space Systems Office at Draper, Alan Campbell is focused on projects and goals that are moonshots in every sense. He has more than 10 years of experience in the aerospace industry in numerous technical and managerial roles. He joined Space Systems in July 2018 to lead the Draper Commercial Lunar Payload Services team, which was selected to provide NASA payload delivery services to the moon, extending Draper's long heritage in support of NASA and commercial lunar initiatives dating back to the development of the Apollo guidance computer. He's responsible for managing business development initiatives and leading proposals and program execution, currently focusing on civil and commercial lunar architecture opportunities, including several elements of NASA's Artemis program. As you can imagine, the intersections of tools, technology, and people that Alan deals with on a daily basis are as essential as they are complex, which is why I'm looking forward to hearing about how he approaches them to literally go out of this world. So please join me in welcoming Alan Campbell.
Thank you. Thanks, Jeremiah. I am honored to be here. And I want to thank everybody for having me and welcome everybody to GeoWeek 2022. Probably like myself, I'm sure a number of you are really excited to get back out into the industry events. I was able to get to a conference or two last year, but it's been a long, lonely winter, and we're excited to get back out there this year. Could we get my slides up? Perfect, thank you. So I want to make two apologies in advance. First, a little rusty. It's been a while since I've been on stage. And second, this is not how I usually dress. My clothes are somewhere between here and Chicago, so hopefully they'll be here before I leave. It is a huge honor to get invited to come up here. It's a huge honor. It's also a little confusing to give the intro keynote to a major industry conference that's not really my industry. And I was confused when Lee and Jeremiah and the Diversified team reached out to me to see if I'd be interested. But the more I thought about it, the more and more it makes sense. We have a lot of interesting connected problems for what we're trying to do going to the moon. And the more really smart, really motivated people to help us think about that is always going to be helpful for us in our execution. So I thought this would be a great opportunity to talk a little bit more about what we're doing to some connected and less connected audience. But it'd be a lot of fun. And who doesn't like nerding out on space? So first, I need to take a little bit of time to talk about my employer, Draper. One is to convince you all that we, and thus I, know what we're talking about. Two, to give a little bit of a perspective, because we do have a unique view on this world, and I'll talk a little bit more about that. And three, they paid for my flight and my hotel, so probably should give them the time. So we are an independent corporation, but also a not-for-profit. So that means that we can do a lot of really different things. So unlike a national laboratory, Sandia, Livermore, MIT Lincoln Lab, we're not a federally funded research development corporation. We can go partner and work on whatever we decide is worth our time. But we're also a not-for-profit, which means that major industry players, Lockheed's, the Boeings, the Northrop Grummans, as well as commercial companies, whether it's SpaceX or whether it's Blue Origin, or all of the hundreds of nascent space companies or other technology companies that we work with, they don't really see us as a competitor. So it really opens up our opportunities for a lot of really interesting problems and a lot of really synergistic cooperations with different organizations. So our founder up here, Dr. Charles Stark Draper, or Doc Draper, seen here getting an award from President Lyndon Baines Johnson back in the 60s, is regarded as the father of inertial navigation. So figuring out where you are absolute within, whether it's on Earth or undersea or in the atmosphere or in space, and then being able to go where you wanted to go from there. And early on, before World War II, he was a recognized leader in just making things work. In those early days, inertial navigation was useful in a lot of different technologies, but two of the most impactful, pun sort of intended, were the guidance systems for the Navy's submarine-launched missiles and NASA's Apollo spacecraft. There are a number of great stories for how we invented or transitioned into these new solutions, but I only have time to tell one today. That is, after Apollo 11, after Neil and Buzz Aldrin walked on the moon and came back, this guy named Neil Armstrong was having a career crisis. So, Neil comes back from Earth, goes through quarantine. He's trying to figure out with NASA what he's going to do next. And he was a trained naval aviator, experimental test pilot, and then astronaut. So he wanted to go fly. And NASA told him, no, you're a national treasure. We cannot let you go fly in space or fly experimental jets again. So after some work, they put him in charge of the aeronautics branch. He was a deputy administrator for aeronautics at NASA. And one of the programs that they were working on that was to try to take the digital fly-by-wire techniques that we had used for Apollo and a few other organizations were developing for smaller aircraft and turn them into a way to be able to fly a big fighter jet like the F-8 more capably. And they were having some issues. So Neil takes over this program and he goes in saying, what's the problem? Well, we're having some trouble getting this to work. It's like, well, go call the guys at Draper. They just flew me to the moon and back using a digital fly-by-wire system. They should be able to figure out how to make this airplane work. And so they did, and we did. And so to this day, any jet that you guys all probably flew here on, like myself, not my bags, flew on a digital fly-by-wire with a triplex voting system built off of what we had developed for NASA on the F-8. Things are a little bit different, though. That back in those days, that's kind of how big programs got to work. Somebody would call somebody and say, hey, can you help me with this problem? Sure, and then go do it. Up here on the top left, that telegram is how we were notified that we were going to be the first prime contract for the Apollo program, to develop the guidance and navigation system or the guidance computer. Now it seems, to me anyway, that the procurement and contracting process is harder than developing the actual technical product. So our contract there was to do the software, the hardware, and the user interface. For a little bit more perspective, the image in the top right, that's our software lead, Margaret Hamilton, with the actual software standing next to her. Punch cards, a lot of fun. Bottom right, that is the computer and the user interface that we developed and flew on the moon. Looks a little bit different than what you've got in your pocket or on your desktop at home, and it had a lot less memory than what you have in your pocket or on your desktop at home. But we got it there and we got the astronauts back. And the other thing to note is I said prime contract for the guidance and nav system. Back then, NASA owned the full mission solution. NASA owned the Saturn V, each of the Apollo modules, mission control, and so on and so forth. And they took everything and put it together and made it work. Here we have an image of a number of the different organizations that provided hardware for the Apollo program, major subsystem and subsystem providers. These days, that's not the case anymore. NASA isn't building the spacecraft or the rocket. They're buying services, whether it's a ride or an instance of a commercially available vehicle. If NASA wants to deliver supplies or crew to the space station, they're buying a ride from Northrop or SpaceX, or someday, hopefully soon, Boeing and Sierra Space. If NASA wants to build a new space station after our current one goes into the Pacific in 2031, like they just announced, they're going to be renting space from ones built by Axiom or Blue Origin or Lockheed and Nanoracks or Northrop. And the reasons behind this change are complex, and it's even probable that this is a better way of operating. Different, but better, especially for the much smaller budgets that NASA has as a percentage of US spending compared to what they did back in the Apollo days. And like I said, it is different, and the industry is adapting in a lot of different ways. One way is to have multiple large or very well-funded company teams. Some examples here. This does force niche technology developers like Draper, and I'm assuming many of you, to act more as component or system providers, especially as many of these large companies have active mergers and acquisitions efforts to pull in key niche technologies in-house. Vertical integration is indeed a pattern. And then the elephant in the room, or at least that I don't have on this slide, is SpaceX. Because to me, they're all in on vertical integration, doing everything in-house beyond just the most off-the-shelf components. But for those that have really cool niche technologies, like us, and like many of you here, there's a ton of innovation happening, and the time is right for outside-the-box solutions. Because another impact of NASA not owning the solutions that they have in their architectures is that much of this innovation is happening commercially. And this innovation, at least in my industry, is extremely well funded, and that funding shows no evidence of slowing down as numerous companies, organizations are working toward building a sustainable space economy. So if you look up on the screen, there's a lot there. There are multiple elements in orbit around the moon. There's the multiple elements there on the lunar surface. And this is just NASA's plan. There are dozens of smaller and larger space companies that are building up their own plans. And if even some of those commercial aspirations take place and occur, the moon is going to be a really busy place in a decade or two. And so there brings a lot of challenges, some of which I hope people like you all can start to help us in the space industry figure some of them out. So let's walk through a couple key mission challenges. So the first is closest to my heart, is lunar landing. One, because that's a big part of my company's heritage, and it's also what I personally have been spending a lot of my time working on over the last 3 to 4 years. So let's talk about the problem a little bit. Lunar landing, regardless of whether you have crew on board, is mostly autonomous or automated process. And that is, so from the point when the astronauts get into their launch vehicle or on top of the launch vehicle until they landed on the moon, in an optimal situation, they didn't touch the control stick until they were about 500 meters from the lunar surface. And even from that point forward, when they were touching the control stick, it was only because the baseline plan didn't work right, or a rock popped up into the landing space. And then we're continuing to develop this forward as we build toward a baseline of even crewed missions being fully autonomous or automated. Because when we go to Mars, NASA has already determined that because the astronauts will have been sitting there for 6 to 8 to 9 months, mostly stationary without a whole lot of physical activity or mental activity, they're not going to be in any shape to be able to land when we get to Mars. So it's going to have to be a fully autonomous practice. So we're trying to develop all of these technologies here and now to test out on the moon and then eventually put in place as we go to Mars. And so some of these issues that we have is we need to know where we are, both in the inertial absolute sense, which we're really good at, but then also in that relative sense to the lunar surface. How high we are, how fast we're going, in order to make sure that we'll be able to control the vehicle down so we can land safely. And we're moving really fast. So we need this information higher than we would for an autonomous driving application or a UAV application. So we need about 30 centimeter precision at the range of 3 or 4 kilometers for our landing map. And we don't have that before we lift off. We have to get that on our way there. Because with the exception of 1 or 2 areas on the moon which we're not allowed to land anymore, we don't have that sort of a priori knowledge. So how do we get this? A lot of sensors, a lot of onboard processing, a lot of onboard computing power and reliance in order to make sure we've got the right solution. And so that brings me to some of these sensors that we want to use. We're looking at camera systems, laser altimeters, radar altimeters, and a lot of different types of LiDAR, which I think is interesting to some of the folks here. Scanning, flash, Doppler, anything that we can do in order to put these different components together so we can have a safe landing on the surface. And we need to be able to get all of this information, put it together in a way that we always know we're going to be right. So multiple systems, computing to votes to make sure the systems are accurate, they haven't been impacted by the radiation environment that we're dealing with, all in time, at least near real time, if not real time, so our control systems can go and control down to the lunar surface. All of this while being light, small, low power, and cheap. Because as we're building a sustainable economy, we want to be able to leverage these systems over and over and over again, both from the system level as well as the component level. Similar in space assembly. So we're slowly getting to the point where we're going to be building up these complex, very similar to the space station modules in a lot of different areas. And then closer to Earth as we go through for refueling applications or satellite maintenance, in space assembly and autonomous rendezvous proximity operations and docking is going to be a huge problem for us. We need to be able to figure out where we are relative to our target spacecraft within the precision of centimeters, all while going tens of thousands of miles an hour. And some of this we can get some help from the ground. Some of it we can get some help with communications directly to our target spacecraft. But in a lot of these cases, like when we're building the lunar gateway on the far side of the moon in a near rectilinear halo orbit, that's going to be a lot harder. So it's onboard systems that are able to identify the appropriate spacecraft to go up and dock to, control, navigate relative to that spacecraft, and all the while going up close enough to the point where you're actually grabbing and docking with it with centimeter scale precision. Do all of this without humans in the loop. That's the tough part now, and that will always be the tough part. Because when we get to the point when we're developing these systems far enough away, the comms delay is going to be to the point where you can't just go and press a button and tell the spacecraft to stop from here on ground in a time that it's going to be able to stop before collision and more bad news. So this is a little bit further away example, but it's a problem that we're working on actively and I think is really, really interesting. And then thinking even further out, how do we live on the moon? And that includes all of the infrastructure that we're going to need in order to develop this, including mining and extraction, additive manufacturing based on materials that we find on the lunar surface, because it is really expensive to try to lift thousands of gallons of water or lead or concrete from the Earth. We've got to go create our own there. Power production and storage. The moon is both okay temperature and really, really, really cold, depending on whether it's in sun or not. And how can we mitigate those temperature swings, also produce our power for the times that we may not have a solar panel able to be able to see where the sun is at? And how do we do this with both people and with autonomous robots in order to be most efficient, interact with each other safely, and be able to build up what we foresee as a lunar base? All of which, while we keep our crew survive, as they are on the surface for weeks at first, into hopefully months and beyond. So these are three key missions that we're really thinking about. We have ideas, we have ways, we have potential plausible solutions, but the better, the more technologies, the more interesting way to think about these problems are always very, very welcome. Anyway, at Draper, we're working on these problems and more in a wide range of application areas, including space, but also underwater vehicles, autonomous airborne vehicles, missiles, other government types of work, biomedical, or MEMS devices, a lot of different technologies areas. And so we're really interested in different ways that you all could possibly help us out with that whether it's in terms of new technologies, new ways of thinking. Oh yeah, or we're also hiring remote, hybrid, in-person roles. Feel free to reach out to me or check our website for details. Once again, welcome to GeoWeek. Thank you very much. Here's Jeremiah.